Welcome back for another video on the polar coordinate system. In this video, we're going to be talking about area. Now, we first talked about area in Calculus 1. So we talked about the area between a curve and the x-axis. We talked about the area above the x-axis being positive and the area below the x-axis being negative. And we could talk about net area or total area. We want to be able to do the same thing with polar curves. But with polar curves, we're not going to be talking about the area between the curve and the polar axis. That doesn't quite have the same meaning. What we want instead is to talk about the area contained inside of the polar curve. So in that sense, we're going to need a different shape. We're not going to be using rectangles. As you'll see, we're going to be using sectors of a circle, wedge shapes, or slices of pizza, if you will. You can also think of them as a fan. So a hand fan that you open up, and the two sides of the fan become the radial arms. And it's going to take all the area right back to the pole, extending out to the curve of the fan, which is going to be our polar curve. So let's go ahead and get started. I'll share my screen with you, and let's talk about how to find area with polar curves. So let's remind ourselves of what we learned in Calculus 1. In Calculus 1, we would take a curve, often, though not always, a polynomial. Could have been a natural log, could have been an exponential. Mostly in Calculus 1, polynomials, occasionally exponentials, or radical functions. And we would take the definite integral of it. Now, the definite integral calculates the area between the curve and the x-axis, so that any area that is above the curve becomes positive, and any area below the curve, like the gray here, becomes negative. And in this way, we were able to estimate, or actually find exactly, the area between the curve and the x-axis by taking the definite integral. Now, we want to be able to do something similar for a polar graph. So for example, let's take a look at one of our polar graphs. So we'll slip down here to example number 5, and we have the graph of a Riemann Sum. So when we get to example 5, this particular problem wants you to find the area inside the Riemann Sum, but not inside the inner loop. So it doesn't want to include the area in the inner loop. That's why it's still white. But it does want all the area inside the Riemann Sum. Now, because the Riemann Sum is symmetric with respect to the polar axis, we're able to sort of cut it in half and compute the area of half of it, and then we'll double it. The problem is, it is truly like a hand fan. So a fan that you slide open like this, and then you fan yourself because you're hot. So when it does this, it comes back to the pole, which is the base of the fan, and then it opens up like this, so that it's getting all the area between one side of the fan where the wood strip is to hold it rigid, and then it goes out in this pattern to where the other fan is. Now, the edge right here isn't going to be exactly a sector of a circle like it would be on a fan. Instead, it's the edge of our polar curve. But the two sides that are forming it are exactly like a hand fan. But that means that you get the area all the way back to the base, which is, of course, the pole, which means that when we do this, we're going to get the area inside that inner loop. So we're going to have to figure out how we can compute this area, and then we'll have to subtract that area off of it. That will give us half of the area we're trying to compute here, and then we'll double it. So let's go back now to our original picture. Right? So what we're talking about is an old-fashioned hand fan like this one, where the base right here is going to become the pole. So the pole is going to actually be at this point right here. So this edge of the fan is going to lay along the polar axis usually, though it may not, right? It may extend in some other direction, and then it's going to extend out. And this edge that you see here, this curved edge for a hand fan, is actually a sector of a circle, or the edge of a circle. ours is not going to follow the edge of a circle. It's going to follow the polar curve. So we're going to have this curved edge be along the polar curve, but it's going to produce two radial lines extending from the pole, and we're going to get the area all the way back to the pole. Now, we may not want all the area back to the pole, so we'll have to figure out ways of taking that area out, as we saw in example 5. So this is basically what we're looking at. Now, because we're using two radial lines, that means that we have two angles, alpha and beta. And those radial lines become the edges of the region where we're finding the area. So just as we integrated on the rectangular coordinate system from x equal a to x equal b, in this particular graph, I believe it goes from -4 up to 11, we're going to integrate in the polar coordinate system between alpha equal to theta equal to beta. So between alpha and beta. And these alphas and betas are going to correspond to the angle that we have this particular picture in. Now, keep in mind that this picture could be rotated. So in other words, it could be rotated something like that, so that my angle alpha is no longer 0 because it's not on the polar axis, it's some other angle. And then I'm going to rotate around and I'm going to be going to beta. So if it were like this, alpha would be from the polar axis up and beta would be from the polar axis around here. Okay, so hopefully that makes sense to you. And let's go ahead now and take a look at the next part. So we turn our attention now to the area in a polar curve, and we want to remember that the fundamental theorem of calculus used the concept of a Riemann sum to approximate the area under a curve using rectangles. Now, ours is a curved region like what you see right here, where the edge is this polar curve, which is like an arc. So more similar to the edge of a circle than it is to anything rectangular. So we're not going to be able to use rectangles, but we can use the same idea from the fundamental theorem of algebra and from the fundamental theorem of calculus, rather, and from the Riemann sum, but we're going to replace the rectangles with sectors of a circle. Now, these are shaped like pizzas or wedges or small sections of a fan that's opened up. So when I look at this graph right here, I can see that it is extending from theta equal to alpha, which is right here, up to theta equal to beta, which is right here. So remember this angle right here, that's alpha. And this angle right here, that's beta. So I'm going to be integrating from theta equal alpha to theta equal beta. And what I want to do is I want to compute the area of each individual little sector. Now, is it exactly the sector of a circle? No, it's not. And the reason is the edge here is not a circle necessarily, although we might have one, not likely. It's a polar curve, but it's close to a sector of a circle. And just as the area under a graph in Calculus 1 was not exactly a rectangle, as we narrowed the width of the rectangles, the shape became more and more accurate and formed along the curve closer and closer. And we're going to do the same thing with these graphs here. We're dividing the region from alpha to beta into a certain number of wedge shapes or sectors of the circle. We'll call them sectors of the circle, even though they're not really of a circle. We'll call them sectors, maybe. So it divides them into a certain number. The formula is exactly what it was in the Riemann sum. You take the ending point where you're integrating to minus the beginning point where you're integrating from, and you divide by the number of sectors that you want. So instead of b minus a over n, we have beta minus alpha over n. And that tells us the width of each angle in each individual sector. So this little measure right here, let me mark it over on this one. Maybe it'll be more clear. This is delta theta, and this is also delta theta. So delta theta is the angle measure of each individual sector. Now, they don't all have to be the same. We found this in Riemann sums as well, but it is true that the widest one has to go to 0 as we increase the number of sectors. So we're going to allow n to go to infinity, which basically means our delta theta is going to go to 0, and those mean the same thing. So n going to infinity, more and more sectors, means the width of each sector is getting smaller and smaller. So we're going to take the area of each sector and we're going to add them together, and that's going to be our approximation for the area that you see here shaded in pink. Now, what we're going to do in order to actually be able to compute that is we're going to use a triangle in order to approximate. So the triangle has a flat end, and if you look closely at the picture here, you'll see that it's not actually going all the way out to the curved section of the polar curve. It's actually got a flat end on it. So what we're going to do is we're actually going to create a triangle, and we're going to find the area of that triangle. And as the width of each individual sector decreases, we'll find that this flat bottom gets closer and closer to the curved edge of the polar curve. So it becomes a better and better approximation, just as we saw when we did Riemann sums with rectangles. The area of that sector turns out to be 1/2 r squared times theta. Let's see why. Now, we know from geometry that the measure of the arc length is r times theta, and this is on a circle. So when we're looking out here and we have some angle coming out from the circle, if the radius is r and the measure of this angle there is theta coming from the center, it has to be a central angle. So coming from the center to the edge, then we know that this arc length, which I'm going to shade here in blue, this curved section of the pizza slice, that is what we call S, and it's equal to r times theta. Now, maybe if you haven't had geometry in a long time, you've forgotten this, or maybe in your class you skipped it altogether and didn't do it. But basically, we can prove through geometry that the measure of the curved section of the circle is equal to the radius measure multiplied by the central angle in radians. Now, this has to be in radians or it's not accurate. So don't be using 90 degrees. So it has to be in radians. All right. So we know that's the measure of the curved arc. Now, we're going to allow our partitions to go to infinity. We're going to have more and more of them. So our delta theta is going to go to 0. Now, our theta is, of course, the delta theta, right? It's the change in the angle. We took the region from theta equal alpha to theta equal beta, and we divided it into n sections. As we allow these to get smaller and smaller, the curvature of the arc becomes flatter and flatter. It becomes less and less. So if you're taking a large section of the circle, you've got a fair amount of curvature there. But if you take a very, very narrow wedge, then that section of the circle that you see at the bottom is flatter. I don't know how else to put it. It becomes closer and closer to the edge of the triangle that connects across here, those two chords. I don't even know if you can see that. It's so close, it's hard to see. So there's a chord that connects between these 2 points on the edge of the circle that makes this into an isosceles triangle. Now, why does it have to be isosceles? Well, because this measure is the radius and this measure is the radius. And when two lengths of a triangle are the same, we call it isosceles. So it does form an isosceles triangle. Now let's look at a wider section. I take something like that, and then I connect these two here. Well, then you can see that the line that connects the two is further away from the curved arc. As you allow that angle to get smaller and smaller, the base of that isosceles triangle gets closer and closer to the curved section. And of course, as we allow the width of that sector to go to 0, delta theta goes to 0, they become the same. And that means that we can use the area of the isosceles triangle to approximate the area of the sector. So let's take a look at this. Now, what are we going to use then to approximate the base of the triangle? Well, the base of the triangle can be approximated with the arc length. And we know arc length is r times theta. So we're going to let the base of our triangle be r times theta. So we have the base of the triangle approximately equal to r times theta. And again, as theta gets smaller and smaller, they get closer and closer to the same value. All right, now the area of a triangle is 1/2 the base times the height. So now we need to form something about the height. So we know already that the base can be approximated with r theta. So let me mark that over here on this one. Actually, that's probably a little wide for our purposes. So let me make it narrower. This curved section right here is r times theta. And again, theta has to be in radians, all right? And we're going to use that to approximate the base of our triangle, all right? Now, the base of our triangle is a different spot, which is going to be, well, let's see, let's make it hot pink. That's the base right there. So when I'm looking at that one, it's hot pink. The base is approximately equal to r times theta. All right, so that base in pink is approximately r theta. What I need now is the height of the triangle. So from the center of the circle down to the base of the triangle, this becomes, as I allow theta to get smaller and smaller, this base of the triangle gets closer and closer to the arc. So the height of the triangle gets closer and closer to the radius of the circle. So hopefully you can see that as this gets narrower and narrower, this line coming to the base of the triangle gets closer and closer to r. So we're now approximating that with r. So let me shade that in blue. So this becomes the height, and it's approximately the radius, all right? So again, now we're ready to look at our formula, which is going to be the area of a triangle. So the area of the triangle is going to be equal to 1/2 the base times the height. So it really is 1/2 of the measure of the blue times the measure of the pink, but that's approximately equal to 1/2, replace the base with r theta, and replace the height with r. And then we can simplify that, and it becomes 1/2 r squared theta. Now, as theta gets smaller and smaller, they get closer together, and it becomes a better approximation. That means that we can use a Riemann sum to approximate the area inside of that sector by adding all of the small areas of each individual sector together of 1/2 r squared delta theta. Now we wrote r as f of theta because in the polar coordinate system, r is the dependent variable and it depends upon theta. So r is a function of theta. So another way of writing this, of course, would be the sum from I equal 1 to n of 1/2 r of theta sub I, the individual delta theta on that particular section, times delta theta, where the width of our sector is delta theta, all right, because that's the measure of the angle inside of our sector. So one of these is one individual sector, adding them all up gives us the area of the entire region. And then you know that this gives us an approximation using sectors of a circle. And then as long as we take the limit as n goes to infinity or delta theta goes to 0, we get the exact area. So we end up with the integral from theta equal alpha to theta equal beta, 1/2 r of theta squared d theta, which gives us this formula that you see right here. Right? So we're ending up with a formula based on r. And it's actually, in a lot of ways, it's a fairly simple formula. You just integrate from the first point of that radial hand fan, so coming out from the pole, alpha, and then around to beta, wherever that is. And that's going to give you all the area back to the pole. And this is the formula that we're going to use. So this is a statement of the formal theorem. We suppose that the function f, which is r, so r of theta, is continuous and not negative on the interval from alpha less than equal to theta less than equal to beta. So when we integrate, just as we do with normal rectangular coordinate systems, we like to integrate from lower numbers to higher numbers. So we're going to do this, and we're going to make sure that beta minus alpha is less than 2 pi. Why? We don't want to trace the polar curve more than once. So we want to make sure that whatever we're doing, we're not going around multiple times. And we also want to make sure that r of theta is not negative, because of course that shoots it out in the opposite direction along that 180-degree line. So as long as this is the case, that r of theta is continuous and non-negative on this interval, and that beta minus alpha is between 0 and 2 pi, so we're not going around multiple times, then the area of the region bounded by r of theta between the radial lines, theta equal to alpha and theta equal to beta, is equal to this integral that you see right there. Now, what's the hardest part of doing these? The most difficult part is twofold. One, there are some polar curves that trace themselves more than once between 0 and 2 pi, in which case you want beta minus alpha to be less than whatever that value is that traces the curve once. So let's say that we have a rose and we get all 3 petals of the rose between 0 and pi. Then you want your beta minus alpha to be less than or equal to pi. So you don't want to go past the point where it starts tracing itself again. So that's one thing to consider. The second thing that makes these somewhat difficult to do is that the value of alpha and beta is not as simple to pick out as it is on a rectangular coordinate system. On a rectangular coordinate system, you just look at the graph and they pretty much usually tell you integrate from x is this value to x is this value, or intersections of 2 graphs. You can find where they intersect. In this case, you're going to have to actually compute where theta equal alpha and theta equal beta are. And that can be the most difficult part. We will use a graphing calculator, and we will also use Desmos in order to do that. On the graphing calculator, using that -0, what I call the key symbol, that option on graphing is very effective, because if you think you've got the right alpha and the right beta, then you can set your alpha as theta minimum, and you can set your beta as theta maximum, and you can watch and see if it traces exactly the part of the polar curve that you want, and then you'll know you've got it. On the Desmos graph, we do the same thing. We'll graph the whole thing first to find out what the maximum value is to get it to trace once, and then we'll set the endpoints so that it graphs exactly the part we're looking for. Now, it can be a little tricky, so sometimes having a slider bar will help you find the correct values. And this is an applet that might help you a little bit. So you can see the directions right here for how to create this applet. So I graphed an r equal 8 plus 8 sine theta and r equal 24 sine theta. And for both of these, I said that theta goes between A and B. Now, setting it like this creates 2 slider bars, one for A and one for B. You want A, since it's on the small end, to be alpha, and B, since it's on the large end, to be beta. Now, looking at this particular one, what we want is we want it to graph from alpha to beta. So we're looking where these 2 curves intersect each other. Now, these two, this one happens to be a cardioid, and this one I believe is just a circle. So we're looking for the area between the cardioid and the circle. So we want to know, where do they intersect? We've got to find those angles where they intersect. So you think you find the right value. In this case, I think A is pi over 6, and I think B is 5 pi over 6. You set those on the slider bar, and then you look to see if it is indeed giving you the shape that is between those two. Now let's take a look at example 1. In example 1, we want to find the area of the shaded region in the cardioid, and the cardioid is given by 1 minus sine theta. So basically, we want the right half. Now, we know from our knowledge of cardioids that they're symmetric, and the question is, we want to be able to integrate from here to here. Now, tricky thing about polar curves. Some students are like, oh, well, that's 3 pi over 2, and that's pi over 2, so I'll integrate that way. No, it has to go from lower to upper. This angle, if we're going to trace in a counterclockwise measure, this one has to be less than this one. So probably we're going to call this one negative pi over 2 to pi over 2. But I have to be sure that that is actually the right one. I mean, maybe this isn't pi over 2. Maybe this is 2 pi over 3. It's kind of hard to tell. This one clearly looks like it's coming straight down. So it's like you open the fan, and that first line is along the negative pi over 2. Let's check it and see if that gives us this point at the bottom. So we're going to check r of negative pi over 2, and that gives me 1 minus sine of negative pi over 2. Remember, negative pi over 2 is this angle right here, and so the sine of that gives me a negative 1, so I have 1 minus a negative 1, which is 2, which puts it right here at the point r equal 2, theta equal negative pi over 2. So clearly that's that one. Now I want to sweep out the area in a counterclockwise way. So counterclockwise is the positive direction. So now I need to go up to this angle here. Now, if I'm going up to this angle here, I need to know what that angle is when it reaches the pole. So notice this is where it touches the pole. Well, at the pole, the value of r is 0. So r of theta equals 0. So what's theta? Well, that means that 1 minus sine of theta is equal to 0, or 1 is equal to sine of theta. And we know that this is when theta equals pi over 2. So it looks like we need to graph between negative pi over 2 and pi over 2. Now you can do this on your graphing calculator and make sure it sweeps out only the right-hand side. Let's look at it on Desmos. So we're going to enter our function, r equal 1 minus sine of theta, right? And there's our cardioid. It's kind of small, so let's make it a little bit bigger, like this. Now we know from the picture that we had that we want this part right here. So first thing I want to check, I look up here, it's going to tell me automatically, Desmos does this immediately, it's going to tell me that from 0 to 2 pi, it traces the cardioid one time. Now I want it to go from negative pi over 2 to pi over 2. I think that's what the values for alpha and beta should be. So I'm going to come up here and I'm going to put in negative pi divided by 2. Oops, somehow I got a point instead of a divided by. And I messed that up. Okay, and I want it to go to pi divided by 2. Right? And now I can see that it is graphing exactly the region I thought it was. Notice that negative pi over 2 is less than pi over 2, and it graphs in one continuous sweep from one to the next. It's very important that when you choose the limits of integration, that they form one continuous sweep in a counterclockwise motion, right? So now we're going to come over here and we set up our integral. So our integral is going to go from negative pi over 2 to pi over 2, and our formula is 1/2 r squared d theta. So r is 1 minus sine theta, and we're going to square it, d theta. Now go ahead and pause the video, compute the integral, then turn the video back on, and we'll compare our answers for the area. So let's see if your answer compares with mine. I ended up with 3 pi over 4. So when I multiplied out 1 minus sine theta quantity squared, I got a trinomial 1 minus 2 sine theta plus sine squared of theta, with the 1/2 still on the front. Then I split it into 3 separate integrals. So 1/2 d theta for the first one, and then 1/2 of 2 is 1, -1. So I get negative the integral of sine of theta. And then the last one is 1/2 of sine squared. But sine squared I know is 1/2 1 minus the cosine of double the angle. So I get 2 theta. And then I integrate each one individually. 1/2 the integral of d theta is 1/2 theta between negative pi over 2 and pi over 2. So I subtract these, that actually doubles them. So I get 1/2 pi. The integral of sine theta is negative cosine, so I get a double negative. That's going to make this plus cosine of theta. So the cosine of pi over 2 minus the cosine of negative pi over 2. But both of these go to 0, so this one zeroes out. Over here, I again have to split the integral into 2 integrals. So I get 1/4 of d theta, which is here, which is going to give me 1/4 of theta, which is going to be pi over 2 minus a negative pi over 2, which ends up giving me pi over 4. Then the last one is going to give me 1/4 the integral of cosine of 2 theta. So I make a u substitution. U is 2 theta, du is 2 d theta is du over 2. I change the limits of integration to u values, so I won't have to go back to theta. And when I plug in, I find that this last one also zeroes out. So I get pi over 2 plus pi over 4, which is 3 pi over 4. So hopefully you got the same result, and it's working out for you at home, checking your answers on Desmos or the graphing calculator. Let's now take a look at the next one. We want to find the area of the shaded region in the rows given by r equal cosine of 2 theta. So remember that whenever the argument to the trig function is even, you get double that number of petals. So because it's 2 theta, we have 4 petals. And in fact, roses are symmetric, which means that the area inside this petal is the same as the area in that petal, and that petal. So I don't specifically have to find the area of that particular petal. I could find that one or that one or that one. It would give me the same value. But we'll go ahead and we'll actually find this one. Now we also can tell, because of the nature of a rose, that this one is symmetric across the polar axis. There's just as much area above the axis as there is below the axis. So we know that in fact, what we could compute is the area of half of that region, and then we could double it. So for example, what I'm talking about is, well, that's not really showing up very well. Let's choose hot pink. I could talk about finding this area right here. And then once I have that area, I could double it. Now, why would this be easier? This might be a little bit easier because this one starts with the radial edge of the fan. Remember, you're opening up a hand fan, and these 2 arms form the angles alpha and beta. And this one is sitting on the polar axis, which tells me that the angle is probably 0. All right. So I want to find out if this does indeed give me this point right here. So I'm going to check it by substituting 0 into the equation. And I want to see if it gives me the radius value that would put it out here. Now, the length of each petal is 1. You can see that from the graph. So I'm hoping this comes out to be the value of 1. So when I plug this value in, I'm testing r of 0 radians, which gives me the cosine of 2 times 0, which is equal to the cosine of 0, which of course is 1. So it is this point right here. This is 1 comma 0 radians. It is also 1, 0 in the rectangular coordinate system, just a fluke. So we have 1, 0 for both systems. Now I need it to curl around in a counterclockwise way. So again, my fan shape. I need it to come all the way around to here. Now, when this angle comes around in here, it's not coming in at an angle of pi over 2. If you're looking at this angle here, it's kind of coming in like this. So that to me looks like it could be pi over 6, maybe pi over 4, but it sure looks like it's on this pi over 6 line. Now I could test that by seeing if that does lead to the pole, or I can look at this particular equation and I can say, when does R hit the pole? When is R 0? So R is going to be 0 at the pole. And we want to know when it comes to the pole the first time after 0 radians. So we're going to take a look. This would mean that cosine of 2 theta equals 0. Now, when is cosine 0? Cosine is 0 at pi over 2 and 3 pi over 2. So at all pi multiples of pi over 2. So we need this 2 theta to be some multiple of pi over 2. Right? So if we add pi to pi over 2, then we get down here to 3 pi over 2, and those values do make cosine 0. So we need to find what theta is. The first thing I do is get a common denominator on the right. So I make that 2n pi over 2. So I get pi plus 2n pi, all divided by 2, equal to 2 theta. Then I multiply both sides by 1/2 so that I can solve for theta. So I get pi plus 2n pi over 4. Now remember, we're looking for theta values, and specifically, we're looking for the first time it hits the pole after 0 radians. So we're going to set up our little chart here. We're going to try n equals 0, and that would give me, looks like, pi over 4. So it was not pi over 6. It looks like it is, in fact, pi over 4. So my picture was a little off. When it comes in, it must be at a sharper angle. So my black is a little off. So I'll redraw that. It's actually coming in at this angle right here. And as I look at it now, yeah, that does look a little bit more accurate. But again, you can't rely on what you see with your eye, because your eye is not accurate enough. I can't really tell the difference between pi over 6 and pi over 4 very easily with the naked eye. That's why we need algebra and calculus. So I got pi over 4. Now it also hits the pole many, many other times, of course. Remember that it will also hit the pole when n equals 1. So that would be pi plus 2 pi, which would be 3 pi over 4. So it must be that this next petal here at the bottom is traced between pi over 4 and 3 pi over 4. And so we can get the different petals coming out, or actually, I believe it's this one to this one. So we can get the different petals coming around between where we can find it. So I could also integrate between pi over 4 and 3 pi over 4. That would work as well. All right. So now what I want to do is I've found that my first angle after 0, where it hits the pole, is going to be pi over 4. So what I want to compute is the area, and the area is going to be double what I have. So it's 2 times, I use the formula, from theta equal to 0 radians to theta equal pi over 4 radians, r squared, and r was cosine of 2 theta. So we have cosine squared of 2 theta d theta. So plugging it into the formula is relatively simple once you have the angles. Now let's go out to Desmos and let's make sure that we do in fact have the right curves. So our formula is r equal cosine of 2 theta. So let's add another one. All right. R equal cosine 2 theta. All right. Now, this is a row. made it very, very small. It's a relatively small rose, right? The length of each petal is 1. So it's relatively small. It takes from 0 to 2 pi to graph the whole thing. So we want to make sure that beta minus alpha is less than 2 pi. We can't go around more than one time. We only want the area once. So we want to know if we can get from here around to here. We just want that part of it. So now I'm going to come up here and I'm going to let that stay 0, but I'm going to make this upper end be pi over 4. And you can tell that it instantly graphs exactly what I think I've got right there. Now, could I also graph the whole circle? Yes, but then I would need to find this angle here. And based on what we did before, algebraically over here, I would be going backwards. So if I were going backwards, this would be n equal -1, and that would give me negative pi over 4. And that would give me the whole petal. So if I changed this end to negative pi divided by 4, you see you get the entire petal. So you can either do half of it and double it, or you can do the whole petal and then use the formula 1/2 r squared d theta. So either way you do it, we have the 2 times 1/2. I chose to do half of it and double it. So these cancel out. I've got a cosine squared. So we're going to make the substitution for 1 plus the cosine of double the angle, and double 2 theta will be 4 theta. So pause the video, work out the calculus, then turn the video back on, and we'll compare results. Let's compare our results. So again, we got the formula. I took half of the area, the upper half of the petal, integrating from 0 to pi over 4. Then I doubled the area. I substituted out the formula for cosine squared. 1 plus cosine double 2 theta is 4 theta. Then I split it into 2 integrals over here. You can see I have 1/2 the integral of d theta and 1/2 the integral of cosine of 4 theta. The next thing I did was u substitution, where u is 4 theta. I got d theta as du over 4. Changed the limits of integration using the relationship that u is 4 theta. When theta is 0, 4 times 0 is still 0. When theta is pi over 4, 4 times pi over 4 is pi. So that changes the limits of integration on the second integral, but not the first. The first gives me pi over 8. The integral of cosine is sine. I evaluate between 0 and pi the u values. Sine of pi is 0, sine of 0 is 0, so the second part cancels out, and I get pi over 8 as the area of 1 petal. So what would be the area of 2 petals? You got it, 2 pi over 8, or pi over 4. The area of 3 petals, well, that would be 3 pi over 8. The area of 4 petals, 4 pi over 8, or pi over 2. So again, finding 1, because of symmetry, we can find the area of more than 1. Now let's take a look at example 3. In example 3, we have both a cardioid and we have a circle. So when we're looking at the cardioid is contained completely inside of the circle. The circle is out here of radius 4, r equal 4, and we know it's a cardioid because these two numbers match, 2 minus 2 cosine theta. Remember, cardioid, cardio means heart, and so it's sort of this heart shape with this definite cusp right there. So what we're trying to find here is the area that is inside the circle, but not inside the cardioid. So how would we find this out? Well, the easiest thing to do is find the area inside the circle, which would be all of it, and then find the area inside the cardioid, and then subtract the area of the circle minus the area of the cardioid, and that should give us the area that we're looking for. So we're going to actually compute the area of the circle minus the area of the cardioid. Now we can also exploit symmetry here, because we know that the cardioid is symmetric across the polar axis. So I have as much area above as I have below. And that might make it easier to compute, easier to find the angles. Or we can use Desmos to see what graphs it completely, and we can graph it all the way around. You can do it multiple ways. all the ways will be the same result. So when we look at this one to compute the area of the circle, don't try to use you can use the formula, but you don't need to. It's a circle. You know the formula for the area of a circle. It's pi r squared, which is going to give you pi, since the radius is 4, it's going to give you 16 pi. Now we need to find the area of the cardioid. So looking at the cardioid, we need to figure out what it takes to trace it, either one full time and integrate that, or find half of the area and then double that area, whichever way you want to do it. The easiest way to do it, of course, would be to start at Desmos or the graphing calculator and see what it takes to graph it once. So 2 minus 2 cosine of theta. Well, let's just change it up here. 2 minus 2 cosine of theta. And we're going to delete these, and that will allow Desmos to choose what it thinks is best. All right. So if we click off, you'll see that it now gives you 0 to 2 pi, which gives you the entire shape. Now 0 to 2 pi is all the way around, and we can integrate 1/2 r squared d theta from 0 to 2 pi. Or we could take half of it, and we could integrate from 0 to pi, and then we could double that area. That would give us half of it. Whichever way you want to do it, I leave it to you to set that up, compute the area, then subtract the two areas. So pause the video, work it out, then turn the video back on, and we'll compare our results. To find the area of the cardioid, I chose to find the area of half of it and double it. So I have 2 times 1/2 r squared d theta, and I'm going from alpha is 0 to beta is pi. Now I went ahead and squared r. Remember, that gives you 3 terms because it was binomial-like. And that gives us 4 minus 8 cosine theta plus 4 cosine squared theta, because the 2 times 1/2 canceled out. I split that into 3 integrals. I have the integral of 4 d theta, which is 4 theta from 0 to pi, so that's going to give me 4 pi. Minus 8, the integral of cosine of theta. The integral of cosine is sine, so I have minus 8, the integral of sine of theta from 0 to pi. But sine of pi and sine of 0 are 0, so this term is going to cancel out. The last one is the cosine squared. So I have the 4 from here, and then I converted the formula with 1/2 1 plus cosine of double the angle, which becomes 2 theta. 4 over 2 reduces to 2. I split this into 2 integrals. So you have the integral of 2 d theta, which is going to give me 2 theta. And so that is going to give me a value of 2 pi when I'm done with it. And then I have the integral of 2 times cosine of 2 theta d theta. So I do a u substitution. U is 2 theta. D theta is du over 2. I changed my limits of integration so I wouldn't have to go back. A lot of students don't do that, but it actually results in fewer mistakes, and it's actually slightly less work. So believe it or not, it's the better way of doing it. Although I would say that maybe 75% of students don't do it that way. So I like to encourage students to do it the more efficient way when I can. So then I integrate this integral of cosine of u. I get sine of u evaluated from 0 to 2 pi. The 2 cancels with the 1/2 coming from d theta. But the sine of 2 pi is 0 and sine of 0 is 0. So this one drops out. And I have 4 pi plus 2 pi, which is 6 pi. Now the 6 pi, of course, that's the area of the cardioid. All right, so that's what I found right here. So then I go back up to the top where I had it written up here in bright blue. The area of the circle turned out to be 16 pi. The area of the cardioid is 6 pi. So the area in between them is 10 pi. All right, let's take a look at example number 4. We have 2 more examples to do. This one is probably the most difficult one out of the entire set. So this one is quite difficult. And I've gone ahead and drawn some pictures here to help us parse out how to figure out this area. Now, why is this one so difficult? Remember that when you find the area on a polar curve, you're using a fan shape. So it's actually opening like this, but it's giving the area all the way back to the pole. And the problem is here in this picture, we do have a cardioid again. In fact, I think it's the same cardioid, 2 plus 2 cosine of theta. And we have a line, r cosine theta equals 3/2. Now remember, r cosine of theta, that's really x. So this is x equal 3/2. So that's what this vertical line is right there. And we write it in the form of r cosine theta equal 3/2. It gives us a vertical line. So when we're looking at this, the problem is the fan shape is going to pull the area back to the pole. So when you look at this picture right here, you can see that it's going to take this blue section right here and include that in the area if you integrate from this angle to this angle. Now there is symmetry, so we can exploit symmetry, which we will do. When we're looking at this one, we'll exploit symmetry again, makes our life a little easier. But looking at this one, the problem is that when we do this, it's always a hand fan shape. And so it's coming back to the pole, but we don't want that area. We want the area on the right side of the vertical line. So we just want the pink shaded area. So what we're going to have to do is compute the combined area of the pink and the blue, and then subtract off the area of the blue. Now, how can we subtract off the area of the blue? Well, if you look at this, this is actually an isosceles triangle, or it will end up being an isosceles triangle. You won't know that yet. But if you compute these two angles where it intersects, these are symmetric, and the value of r at both is the same. Now, in order to figure that out, you're going to have to compute this point and this point right there. So you need to know, when do those two curves intersect? So let's go ahead and find the point of intersection. All right, so the first thing we're looking for is when the cardioid intersects the line. So we have r equal 2 plus 2 cosine theta. This is the cardioid. And we have r cosine theta equal to 3/2. Now, to find where they intersect, we need to set them equal, but I can only set the same variable equal to itself. So I need to solve them both for r. This is already solved for r, but this one is not. So I'm going to take this one and I'm going to rewrite it as 3 divided by 2 times the cosine of theta in the denominator. Now I've got them both solved for r, so I set the two equations equal to each other. So this gives me 2 plus 2 cosine of theta equal to 3 divided by 2 cosine of theta. So I'm trying to get to a point where I can tell what theta needs to be to make this a true statement. Now I've got this 2 cosine of theta, which is going to make my life really, really hard. So first off, it's clear that, I shouldn't have this coming out to be 0 in the denominator. So we're going to go ahead and multiply by 2 cosine of theta on both sides of the equation. So I'm going to multiply everything by 2 cosine of theta. So this gives me 4 cosine of theta on the left. So I'm distributing that times that. And then I'm going to distribute here. So that's going to give me plus 4 cosine squared of theta. And then on the right, it just gives me 3, right? So I've got 4 cosine theta plus 4 cosine squared theta equal 3. Now, you may look at this and go, I have no idea where to go from here. Try u substitution. So let's make cosine of theta be u. So if I let cosine of theta be u, I have 4u plus 4u squared equal 3. That looks like a polynomial equation. I can rewrite this in a different order as 4u squared plus 4u minus 3 equals 0. What do you want to bet? That it factors. And in fact, it does factor. So when we factor this, I'm going to split up the first one as 2u and 2u. The signs in the middle are different, but the larger product is positive. So this has got to be a 3 and this has got to be a 1. That gives me 2u and 6u. The difference is 4u. So this has to be a plus and that has to be a minus. So I have 2u minus 1 equals 0, or u equal 1/2, or 2u plus 3 equals 0, or u equal -3/2. So these are my two possible solutions. Now back substitute for what u is equal to. So u in this case was cosine of theta. So I have cosine of theta equal 1/2, or cosine of theta equal -3/2. Now the second one has to be extraneous because there's no way a cosine is going to be anything outside of -1 to 1. So it can't be a -3/2. So that one doesn't provide a solution, but this one does. Now we want to think about, when is the cosine going to give me 1/2? To be 1/2, it's the narrow side of a 30, 60, 90 triangle, which must mean it's taller than it is wide. So it's got to be a 60 degree. So it's got to be a pi over 3. So cosine of theta is equal to 1/2. And let's think about our unit circle right here. And we're going to superimpose the axis onto it. So this could be this angle right here. So this would give me a positive 1/2. Or this angle right here, which would also give me a positive 1/2. So this could be pi over 3, and this could be negative pi over 3. In both cases, the cosine is going to be positive because x is positive in quadrant 1 and quadrant 4. So I believe that it intersects here at negative pi over 3 and at pi over 3. So I think that's the value that I've got right there. Now let's go ahead and try that in each of our equations. R equal 2 plus 2 cosine of theta. Let's find out what that point of intersection is. So when we're looking at this particular value, we have, let me see if I can write it down here. R equal 2 plus 2 cosine of pi over 3. We know that's a 1/2. So we get 2 plus 2 times 1/2, which is going to give us 3. Now the cosine of negative pi over 3 is also 1/2. So r of negative pi over 3 is also going to be 3. And that means that this point right here is 3 negative pi over 3. And this point up here is 3 pi over 3. Now, how could we figure this out and absolutely be sure that we've got the right points of intersection? By graphing it on Desmos or a graphing calculator. The problem with Desmos and the graphing calculator is it doesn't graph points in polar coordinate systems. But I know that this is also on the vertical line. And I know the value on that vertical line is x equal 3/2. So if I know that's 3/2, I should be able to figure out what the y value of it is. So how could I find the y value of it? How could I figure that out? And then I could be sure that I've got the right two angles by looking at the value. So I'm looking at this part right here. I figured out the two different points. I know this is 3 pi over 3. And this one down here at the bottom is 3 negative pi over 3. And I want to know what that is in rectangular coordinates because I can plot rectangular coordinates in Desmos. And then I can check and be sure that I'm absolutely correct. The other thing I could do is create slider bars, and I could graph the two regions between A and B, between negative pi over 3 and pi over 3, and that would work as well. But I wouldn't be able to check without knowing for sure what the coordinates of that point are. So I'm looking at this triangle right here. I now know it is isosceles because I've got this measure is 3 and this measure is 3. So I know they're both 3 along this side. And I know this measure right here along this edge has to be 3/2. And I know that because this vertical line is x equal 3/2. So I know the radius, which is 3, looking at it like this. and I know this edge is 3/2, I should be able to find this height right here. So coming over here and looking at that triangle, what we have here is that's 3 and that's 3/2. And I want to know what the length of that side is. Now, I don't actually need the angle yet to figure that out. I can figure that out by using the Pythagorean theorem. I know this is a vertical line and this is the polar axis, which is the positive x-axis. So I know they're at right angles to each other. So I can use the Pythagorean theorem. So this is going to give me 3 squared minus 3/2 squared is going to equal the height squared. So this gives me 9 minus 9 over 4, which is equal to the height squared. The height is going to be the square root of, well, let's see, that would be 36 minus 9. Trying to find. So that gives us 27 over 4, which is going to come out to be 3 square roots of 3 over 4. So this height right here in rectangular coordinates has to be 3/2, 3 square roots of 3 over 4, right? Let's go graph the two graphs and see if this is coming out correctly. So we have 2 plus 2 cosine of theta, I believe. 2 plus 2 cosine of theta and x equals 3/2. Okay. 2 plus 2 cosine of theta. So it was almost what we had last time. Cosine of theta. And we want to graph the normal region. So there's our graph. And now we want to graph x equals 3/2. So x equals 3 divided by 2. So now we have that line right there. And looking at this particular one, we want to plot the point where we think they intersect. And we believe they intersect at 3/2, comma, 3 square root of 3. Oops, I hit a 2. Divided by, what was it? 4? Oops, that shouldn't be a 4. I didn't take the square root. That should be a 2. All right. All right. So over here, this should be a 2. Bingo, we've got it. All right. Now this one down here would be the same, but it would be the negative of it. So we can copy this, paste it down below, and change the sign to a negative. And now we've got the one at the bottom. We can tell that is where the two are intersecting. Now, if we want to be sure we've got the angles correct, we could put in here between negative pi over 3 and pi over 3 and see if it gives us that fan shape. So we'll do negative pi divided by 3. And we'll take this up to pi divided by 3. And now we can see we do have exactly that region. It looks like a circle. It's not a circle. It's part of a cardioid. So you can't use a circle in order to figure out what the area inside there is. All right. So hopefully this makes sense to you, what we've done so far. We know we've got the right region. We know we have the right angles. So how can I take this area and take it out? Because when I compute the area, the way that it works in polar coordinates is it sweeps out the entire arc all the way back to the pole. So I'm getting the blue plus the pink. So what I want to do is I'm going to integrate from negative pi over 3 to pi over 3, and that will give me blue plus pink. And then I'm going to subtract the area of the blue. Now, the area of the blue can be computed using the formula for the area of a triangle. So the area of the blue is going to be twice the area of one triangle because I've got 2, the upper and the lower. So 2 times 1/2 base times height. And the base is, so this is going to be 1. The base is going to be 3/2. And the height is 3 square roots of 3 over 2, which gives me 9 square roots of 3 over 4. So that's the area of the blue that I'll need to subtract off after I do the area using polar coordinates. So now I'm going to do the area using polar coordinates. This time, just for fun, we won't exploit symmetry. We'll just go from negative pi over 3 to pi over 3, and then it will be 1/2 r squared d theta. Now, I could also go from 0 to pi over 3 and then double it. And then our formula is 2 plus 2 cosine of theta, quantity squared d theta. So this is going to give me the area of blue plus pink. And I only want the area of the pink. So when I'm done, I'll subtract this from this, and that will give me the area of the pink only. So now I've got 1/2 integral from negative pi over 3 to pi over 3. And this gives me 4 plus 8 cosine of theta plus 4 cosine squared of theta d theta. Now I've got a 4 in common here, so I can factor out the 4, and that's going to give me 4 times 1/2, which will be 2. So this becomes 1 plus 2 cosine of theta plus cosine squared of theta. So now I can split this up. So 4 times 1/2 gives me 2. So I have 2 the integral negative pi over 3 to pi over 3 of d theta plus, now I've got 4 over 2, which becomes 2 plus or times 2 cosine theta, which gives me 4 the integral of cosine theta d theta. And then I'm going to have 2 times the integral of cosine squared. But cosine squared becomes 1/2 1 plus the cosine of 2 theta d theta. This is from negative pi over 3 to pi over 3. So the 2 times 1/2 cancels, and I get a 1, right? If you want to pause the video, you can pause the video here, work out the rest of it, and then turn the video back on, and we'll compare our results. So hopefully you're not too frustrated by all the integration that takes place. The actual concept and the implementation is not too difficult once you get the angles, and the rest of it is just computation. So when we're looking at this one, again, we have to square the radius. This time I integrated from negative pi over 3 to pi over 3. It actually made my life more difficult. If I'd exploited symmetry and gone from 0 to pi over 3, it would have been easier. So again, I do that for demonstration purposes to convince you to exploit symmetry when you can. So I multiplied it out. I factored out the 4. 4 times 1/2 gives me 2. So I split it into 3 integrals, 2 d theta, and then I've got 2 times the 2, which gives me 4 cosine of theta. And then I've got the 2 cosine squared, but I convert the cosine squared into 1/2 1 plus cosine of 2 theta. Now the 2 and the 1/2 on that are going to cancel, and I'm going to get a 1. So I'm going to do a u substitution on that last one out there, where u is 2 theta, du is 2 d theta, so d theta is du over 2. Changing the limits of integration, u goes from negative 2 pi over 3 to 2 pi over 3. Then I split this integral into 2, so I get another d theta here and a cosine of 2 theta. If you were careful and you were paying attention, you could have added these 2 together to get 3 d theta before you integrated, but I didn't. I wasn't paying attention, and so I integrated them individually. The integral of cosine theta is sine of theta between negative pi over 3 and pi over 3. Sine of pi over 3 is square root of 3 over 2. Sine of negative pi over 3 is down in quadrant 4, so it's a negative square root of 3 over 2, giving me a double negative. So these double, so I get square root of 3. So when I'm done with this section right here, I have what results below it. So I have 4 square roots of 3 from this part. And then I have theta between negative pi over 3 and pi over 3 from the additional integral of d theta, which is going to give me 2 pi over 3 down here. And then I have to integrate cosine of u. And I change the limits of integration to u values. The integral of cosine is sine. I still get a 1/2 because d theta was du over 2. So I have a 1/2 sine of u from negative 2 pi over 3 to 2 pi over 3. Now 2 pi over 3 is around in quadrant 2, but it does have a value of negative or positive square root of 3 over 2. So you get this value right here. And then negative 2 pi over 3 is going to be actually around in quadrant 3. And because it's in quadrant 3, it has a negative value, negative root 3 over 2, but that gives me a double negative. So again, they double. So I get half of the square root of 3, which you see down here. Get a common denominator between these two. It's going to be 2. This becomes 8 square roots of 3 over 2 plus 1 square root of 3 over 2 is 9 square roots of 3 over 2 plus the 2 pi we got from the first part. Now, this represents the area of both the blue triangle and the pink region. So let's go back up here again and remind ourselves why we get both. When you do the area of a polar curve, it sweeps out the region all the way back to the pole. So you're getting this blue in addition to the pink. We only want the pink. So what we did was we computed the area of the blue by using the triangle. And we found that the area of the blue, when we doubled it, we got 9 square roots of 3 over 4. So we want to subtract that from the area we found for both the blue and the pink. So coming down here to the bottom, we have the area of the blue and the pink, which we found here to be 2 pi plus 9 square roots of 3 over 2, minus the area of the blue triangle, which is 9 square roots of 3 over 4. You need a common denominator, which is 4. That makes that 18 root 3 over 2 minus 9 gives us 9 root 3 over 4. All right. So we have 2 pi plus 9 root 3 over 4. And that's the exact value of the area of the pink region to the right of that vertical line. We have one more example to do. This is the one that we looked at the very beginning. And this is the one where we want to find the area inside of the Riemann Sum, but outside of the inner loop. Now, the equation is 1/2 plus cosine of theta. So this is definitely a Riemann Sum because the coefficients here are different numbers. This is 1/2 and this is 1. And so this gives us a loop, an inner loop Riemann Sum, where the 1/2 is smaller than 1. That's what gives us the inner loop. So we want to find the area of the pink shaded region. But we know that if we integrate all the way around, it's going to give us the whole thing. So what we're going to do is we're going to exploit symmetry again, and we're going to go halfway around, which is going to give us this region right here. But it's going to give us this shape that you see down here. So it's going to include that hole. Now I've got to figure out how to go from here around to here. I need to find those angles. Now coming out here, it looks pretty clear. It's probably at the angle theta equal to 0. But let's check it and see. We can tell from the graph that that's at 3/2. So if I plug in 0 for this, I do in fact get 3/2. So that is that point right there. What about this one? Well, it's coming in at a relatively steep angle. It's not entirely clear what it is, but if I kind of draw across it as it comes in, I'm going to guess 2 pi over 3, but I don't know that. I can't tell that well enough from the naked eye, but I'm guessing 2 pi over 3. It looks like this angle as it comes around, sweeps around, that it hits here. How do I know for sure? Well, I can always use Desmos. I can use the graphing calculator, and I can use algebra and calculus. I need to know when it hits the pole. It hits the pole twice. So it sweeps around here, bam, hits the pole. Makes the inner loop, bam, hits the pole again. So it hits the pole twice. So I want to know, when does it hit the pole the first time? So to hit the pole, r equals 0 at the pole. So now I'm going to find the equation where r is 0. So that means 1/2 plus cosine of theta equals 0, or cosine of theta equals negative 1/2. Now, this is just theta, so I don't have to worry about the ends too much. When does cosine give me a half? Well, it's got to be a narrow but tall triangle of the 30, 60, 90. So it's got to be a multiple of pi over 3. It's negative, so it's got to be in quadrant 2 or 3. And I already suspect it's in quadrant 2. And I suspected 2 pi over 3. And this just reassures me that, yes, it is 2 pi over 3. So this would be theta equal to 2 pi over 3. Where's the next time it's going to hit the pole? Well, that would be this angle right here, which would be 4 pi over 3. That's the other time when r is going to be at the pole, because the cosine of the angle is negative 1/2. So again, the reference angle is pi over 3, so it gives us a cosine of 1/2. It's in quadrant 3, so it makes it negative. So it hits the pole twice, 2 pi over 3 and 4 pi over 3. And again, I'm trying to go in order of when it hits the pole. So I want the sweep from 0 around to 2 pi over 3, which is going to give me this entire pink shaded region. Now that's only half the area, so I'm going to have to double that to get the full inside the whole cardioid, and then I'll have to subtract out the whole. So first I'm going to find this area. So I'm going to get the area inside entire Riemann Sum. Is going to be 2 times the integral from 0 to 2 pi over 3 of 1/2 r squared, which was 1/2 plus, I think, was it cosine of theta? Yeah. Cosine of theta squared d theta, right? That will give me everything shaded in, including the whole. And then I'll have to subtract out the whole. So this is going to cover everything into pink. So if I compute this one, you may want to go ahead and pause the video, work out the algebra and the calculus, and then turn the video back on, and we'll compare our results for the area inside the Riemann Sum. Let's compare our results. So we're finding the area inside the entire Riemann Sum by doubling the area from 0 to 2 pi over 3, which sweeps out the entire thing from the pole out to the edge of the curve. So we have 1/2 of r squared d theta. So the 2 times the 1/2 cancels. When we square the binomial-like thing, we get 1/4 plus cosine theta plus cosine squared of theta, which we've had a bunch of times today. And then we go ahead and split it into 3 integrals. We convert the cosine squared using the double angle formula. We make a u substitution for u equal to 2 theta, which we've done multiple times. We convert the limits of integration from theta values to u values. U goes from 0 to 4 pi over 3. Now this time I was paying attention a little bit, and I knew this is going to be a 1/4 d theta. And I knew this, when I split it into 2 integrals, was going to give me a 1/2 d theta. So these two have the same limits of integration, and they have essentially the same integrand, differing only by the constant. If they have different limits of integration, I couldn't combine them. But in this case, 1/4 plus 1/2 gives me 3/4. So coming down here, I'm basically integrating 3/4 d theta from 0 to 2 pi over 3. The integral of cosine gave me sine, evaluated between 0 and 2 pi over 3. The sine of 0 is 0, but the sine of 2 pi over 3 is the square root of 3 over 2. Again, integrating cosine is going to give me sine. And so over here, I have 1/4 the sine of u. Remember, we still had the 1/2 from converting to the double angle, and d theta became du over 2, so I end up with 1/4. And I changed the limits of integration to u values. Again, the sine of 4 pi over 3 is around in quadrant 3, so sine is a negative root 3 over 2. Sine of 0 is 0 again. So when I work this out, I end up with pi over 2 plus 3 root 3 over 8. That's making the whole thing inside the Riemann Sum entirely solidly pink. What we want to do now is find the area inside the hole and subtract that out. So we already know from what we did before that it hits the pole twice at 2 pi over 3 and 4 pi over 3. So the first time is at 2 pi over 3, and then it continues around and hits at 4 pi over 3. So if I integrate from 2 pi over 3 to 4 pi over 3, I'm just getting the little inner loop here. So let's look at this on Desmos so that you can see that I'm only getting that part of it. So I'm going to open up a new screen. So we have R equal 1/2 plus cosine theta, I believe. All right. So there is our inner loop Riemann Sum. It's relatively small, right? So the maximum is out there at 3/2, which we found earlier. So we've got this right here. Now we want to be sure that if we integrate from 2 pi over 3 to 4 pi over 3, that we're just getting the inner loop. So we're going to change the lower to 2 pi divided by 3. And we're going to change the upper to 4 pi divided by 3. Now you can see that I only have the whole. So if I do the area formula for this, I'll get the area inside the whole. Now I want to exploit symmetry again because it's symmetric with respect to the polar axis. So I want to go halfway around. So if I go halfway around, where would I be going? Well, what's halfway between 2 pi over 3 and 4 pi over 3? Pi. So I could go from 2 pi over 3 to pi, or from pi to 4 pi over 3. But you have to go in order. So again, if I go from 2 pi over 3, I could then go to pi, and that would just give me half of it, and then I double it. Now remember, this is always giving us the absolute value of area, so we're going to be able to integrate from 2 pi over 3 to pi. So now I'm going to find the area of the whole, or the inner loop. I guess that would be a better way of naming it. The area of the inner loop of the Riemann Sum is going to be double 1/2 the integral from 2 pi over 3 to the larger angle pi, 1/2 r squared, so 1/2 plus cosine of theta squared d theta. All right, now I've already multiplied that out, and I've already integrated a lot of this, so I can use what I've done before. I just need to change the coefficients appropriately. So go ahead and pause the video. Remember that the limits of integration have changed as well, so you'll have to do the ending part again. So pause the video, work it out, and then turn the video back on, and we'll compare our answer. So let's compare our results. What we had just found was the area of the entire thing, the whole inside of the Riemann Sum shaded pink. Now we need to take out of that the area of the inner loop. So the area of the inner loop is going to be double if I take half of it. Half of it goes from 2 pi over 3 to pi, or you could do pi to 4 pi over 3, either one of those. So then I squared this, which I've done before, so I already know what it turns out to be. 2 times 1/2 cancels. I split this into 3 integrals, substituting out the cosine squared for 1 plus cosine of 2 theta. And then I went ahead and worked these out separately, even though I could have done them together. I didn't think it saved me that much time. And then I did a U substitution, which I've done multiple times on the same thing. So when I did the U equal 2 theta, I changed the limits of integration, and they became 4 pi over 3 to 2 pi for U values. When I plugged all of this in and simplified it, I got quite a bit of simplification. The sine of pi is 0, but the sine of 2 pi over 3 is not. It's square root of 3 over 2. So that gave me a negative square root of 3 over 2. Pi minus 2 pi over 3 is 1 pi over 3, which becomes pi over 12. And then for the next one, I have 1/2 of theta times pi minus 2 pi over 3, which is going to give me pi over 3. So this is going to give me a pi over 6 in the next line down. And then in the last part, I needed to integrate this 1/2 cosine of u. And then I replaced d theta with du over 2, which gives me a 1/4, and the integral cosine is sine. Notice the change in the limits of integration. The sine of 2 pi is 0, so that one drops out. But the sine of 4 pi over 3 is a negative root 3 over 2, but it's a double negative, which will make it positive. So that's going to give me square root of 3 over 8 when I multiply by the 1/4. Then I can add these two together. They're like terms. That gives me 3 pi over 12, which reduces to pi over 4. Multiply this one by 4 over 4, and I get negative 4 root 3 over 8 plus 3 over 8, which gives me negative 3 root 3 over 8. That's the area just inside the inner loop that we found on Desmos. So that would be this one going up to 4 pi over 3. So we found that area right there to be this value. Now what we want to do next is we want to compute the area of the Riemann Sum minus the area of the inner loop. So we take the value we got for the entire area and we subtract the area for the inner loop. You need to distribute the negative, combine your like terms, and the final result is pi over 4 plus 3 root 3 over 4. I hope that you have enjoyed learning about these fascinating types of functions and that you understand now how polar coordinates can be easier for certain shapes than for other shapes. What we want to do in the last section in our next video is we want to look at particular shapes which are much more easily done and described in the polar coordinate system rather than the rectangular coordinate system. And these are the primary conic sections. That would be the parabola, the hyperbola, and the ellipse, circle as well. So we're going to be looking at these and how you represent those equations in the polar coordinate system. We will review what it looks like in the rectangular system just to bring everyone up to speed, make sure you're understanding the different parts, and then we'll look at the equations in the polar coordinate system. I hope you'll join me for that next video.